next part. Okay, so few more thing about the OpenFOAM we're going to explore here. Okay, so here again it is about this getting started and exploring the OpenFOAM. Okay, so it is basically based on the finite value method. Okay, so entire coding, entire platform what we see as OpenFOAM is based on the finite volume. Okay, it able to work with the polyhedra type of the unstructured mesh. Okay, so you need not to worry about any type of the element. You can work with the hex, tet, okay, polyhedra, any type of hybrid mesh, okay, unstructured, structure mesh. It able to adapt your all the meshing. Okay, and beauty about the OpenFOAM is that it is parallel. Okay, you throw any mesh, it going to work in the parallel environment. Okay, second order accurate in space and time. This type of the discretization is available. Okay, and some class of the higher order discretization methods is available. Pressure velocity coupling is something like piezo, and simple type of the algorithm is available, and if you blend both of them, it's called pimple in the terminology of OpenFOAM, that is available. Coupled solver are under active development. Okay, so people are developing something like coupled solver. This is all called the iterative solver, where step by step we iteratively try to solve one equation after another, but when we talk about the coupled solver, at a time Navier-Stokes energy equation solved together, so it is much faster solvers. Okay, it is parallel by default, so you can throw the OpenFOAM in either in a shared memory and it is supposed to in a distributed memory environment. Okay, because when we talk about this shared memory, but shared memory, let's say you have PC of something like multiple processors, okay, like Xeon server or something with 8 to 10 core, immediately you can fire the run on that. If you have a cluster, like let's say you have a something like a Xeon base 8 to 10 blades are combined, and you want to run something like 100 cores of simulation, you can do that as well. Okay, it come with its own mesh generation tools like SnappyHex and BlockMesh. Okay, it come with many mesh manipulating utilities. Okay, so either you create your own mesh with some mesh generator like ICM CFD, okay, or let's say Hexa mesh with some open source mesh generator, or let's say Hypermesh is the very good mesh generator, or you have your own mesh generator, you use that mesh generator, okay, and you try to export that mesh in the compatible form that OpenFOAM can adapt. Okay, but I will tell you, OpenFOAM right now is able to take a mesh from the giant mesh generator like ANSYS any mesh generator. Okay, star CCM, if you have a star CCM, you generate the mesh and OpenFOAM going to adapt. Okay, COMSOL mesh, it going to adapt. Okay, so like that way, so many mesh options is available. It's not necessary you generate the mesh in the OpenFOAM and only adapt that mesh. Okay, many other mesh generator can convert in the form of OpenFOAM. That is how you can see all component implemented in library form and easy to use. Okay, physics wise, if we see, okay, thermophysical models like Newtonian, non-Newtonian models is available, liquid gas phase available, transport models like rheology available. Okay, turbulence modeling capability, if you see, RANS, DNS, LES, okay, all thing available. Lagrangian particle methods are available. Okay, discrete particle modeling available, VOF for multi-phase flow available, interface momentum transport model for multi-phase available, combustion, flame speed, chemical reaction, porous media, all these models, physical models are available. Okay, now let's explore certain readily available out of the box solvers. When I say readily available out of the box solver, that means all these solvers is available. You just have to run this solver and you can execute your own test case. Okay, so basic solver wise, if you see, Laplacian, potential flow, passive scalar transport available, compressible, incompressible flow base, if you see, then simple is the algorithm and piezo is the algorithm. Based on simple and piezo algorithm, there is a solver available in it. Heat transfer modeling capability, buoyancy driven, conjugate heat transfer. If you are looking at conjugate heat transfer, that class of solver is also available. Multi-phase wise, if you look at Eulerian, VOF, that is for free surface, multi-phase flow, cavitation, phase change, all this thing is available. Stress analysis, electromagnetic, acoustic, MHD, fluid structure interactions. So all this multi-physics class of solver is also available, ready to go. But here is the catch. let's say if you are interested in fluid structure interaction, okay, FSI, then FSI is not readily available in the distributed version, but it is available in extended version of the OpenFOAM. That's why if you see at the beginning I show you two version of OpenFOAM is available, Form 3.0 and another is FE4. So it is extended version of the solver, okay. So on the pen drive almost all this physics be able to execute, okay. When we talk about this solvers, okay, so we see certain out of box all the solvers is available. That is not enough. Let's say why it is not enough, because based on our application this readily available solver not going to work, okay. So for that we have to develop our own solver, okay. So we can develop our own solver, okay. OpenFOAM is designed to be a flexible and programmable environment for a numerical simulation by using higher level programming language, that is direct representation equation being solved. So what is equation being solved is something like this way. So if you see, this is our normal equations, okay, and if you want to code this equation, then we require that many line only, okay. So solve, this is FVM, okay, finite volume base part, okay, and this is the DDT rho u, okay, this is divergence, okay, this is Laplacian, and this is a gradient. So if we want to, let's say, write a solver for these equations, okay, we have to write this only 4 line, that's it, and with the help of that you are able to code this. So you need not to think what discretization method I going to use. Either you go with Eulerian implicit, explicit, Crank-Nicolson, backward, anything you use for temporal, for let's say convective part, second order center difference, upwinding scheme, quick scheme, you need not to think while you are developing your solver. Why? Because when you say divergence of flux and u, okay, it will understand whatever the scheme you are going to select, it immediately apply the discretization here, and all the scheme discretization schemes is coded in terms of the libraries, okay. So that library is readily available, okay. You based on the calling of particular scheme, it immediately add up that part, okay. Same way Laplacian, immediately whatever the scheme you're going to add up, it going to work with that, okay. So different, so it is very easy to understand the code. So when you walk through the code, you will see this type of the syntax, okay. So you understand DDT, that means this is temporal term, divergence term, Laplacian term, and a gradient term. It's very easy to look at all these things, okay. So FVM and FVC, okay, finite volume method and finite volume calculus. But if you look at inside, other concept is the implicit scheme, implicit and explicit. What it means, FVM wherever it is implicit, and FVC it always explicit. That means whatever the pressure we going to use for this gradient, it coming from the previous time step or from the guess value, and all this come in terms of the implicit environment, okay. So where you write whatever the term you require in the implicit, you type VEM, whatever the term you require in the explicit way, you type as a VEC. That is how you can code any class of the equation. So it is called equation mimicking syntax, okay. It is very handy, and it is very simplified way to write your own code, okay. So equation mimicking syntax achieved through use of object oriented programming enable user to create custom solver with relatively easy. If you are aware, or if you have any idea about solver development, so if you want to develop your own solver for, let's say, simplified finite difference method base with a simple algorithm, I think you require something like more than 6 month time frame to develop this class of the solver, okay, because that is what I spend time when I develop my own solvers, okay. And when you look at entire of this solver, you come with something like more than 2000 3000 lines of code. But if you look at here, you required hardly few lines of the code to finish your entire solver, okay. So if you are thinking to develop your own solver from the scratch, I say no, add up the OpenFOAM, understand the OpenFOAM, and start with OpenFOAM and develop your own solver, okay. So OpenFOAM is coming with the library form, reusable form. As I told you, whatever required, immediately adapt, okay. Let's say turbulence model, whatever the turbulence model we want to require, just adapt in terms of the libraries, okay. So solver can be tailored by the user for a specific need. OpenFOAM is ideal for research and the development prospect, okay. Top level solver are written in few hundred lines of the code and are optimizable and efficient, okay. That is what we can say. So if you look at this entire OpenFOAM, okay, it's assembled as a component wise. Okay, so fundamental libraries or fundamental platform is available in terms of vector and tensor algebras, mesh handling, discretization methods, boundary condition, linear solver, parallel computing environment. It is like some type of the basic platform, and over that we try to create our own application, our own libraries. Okay, physical modeling libraries, utilities and solvers are available. Okay, all application utilities are compiled using common functionality in the collection of libraries distributed with the OpenFOAM. With the one command you can compile all the library. If you want to compile step by step, you can compile as step by step. Okay, this ensures the consistency across the whole of the OpenFOAM distribution rather than having a pit and bust. Okay, that means and everything is one to one linked. Okay, and you can develop your own link. Okay, you can separate the link and you can create your own solver. It is very, very important working with the OpenFOAM. Transparent solution algorithm, whatever is we going to simulate, immediately you can explore. Let's say we are going to work with the simple form, immediately go and check how the simple form algorithm is look like. Okay, this is one very important classic statement from JSAC. Okay, OpenFOAM is an excellent piece of C++ and software engineering, decent piece of C++ code. Okay, so that is what he put this statement. So this is very simplified way of looking the OpenFOAM. Let go towards some standard capabilities that is available with the OpenFOAM. Okay, very quickly we walk through this. Okay, so basic solver wise, if you see, then Laplacian form solver for a simple Laplacian equation like a thermal diffusion in a solid. Potential form, if you aware about potential equation, it is nothing but it is just a potential solver to solve a potential equations. And where are we going to use it? To create a initial condition for a complete Navier-Stokes equations. Okay, so that is how you can see as a potential form. Scalar transport form, it is nothing but any type of the transport for any type of the scalar. If you want, then stick to this scalar transport form. Okay, simple form, so it is a steady state solver for incompressible turbulent flow. Okay, so it is when you are looking at a steady state type of the simulation, try to stick with the simple form. Okay, and if you are looking at purely, let's say, incompressible turbulent, if you require the laminar, no worry, with the help of simple form, with one switch we can shift towards the laminar as well. Okay, ICO form, transient solver for incompressible laminar flow on a of a Newtonian fluid. Okay, if you want laminar flow in the transient environment, then go toward ICO form. Okay, if you want, let's say, transient solver for incompressible flow, go towards piezo form. But piezo form has a certain limitation, so when we go towards let's say highly complex physics, then try to stick to the pimple form. Later on we try to explore what is the difference in between, but when we go toward pimple form, you have a leverage to go towards larger time step. Okay, that is how I can see. Non-Newtonian ICO form is available for non-Newtonian fluids. Okay, channel form for LES type of the applications. Porous simple form is available. Okay, optimizer, step optimizer type of the form is available. Okay, boundary form is available to create certain class of the boundary layer type of the boundary condition. MRF simple form is available. Pimple dynamic form is available. Pimple, okay, sorry, it's repetition. Look, couple of the solver, maybe you will not get directly in the distributed version, but if you Google it, you will get a source code available in certain class of the hosting. Okay, so that's why I summarize certain few more things here. Shallow water form, transient solver, inviscid shallow water, SRF, steady state solver for incompressible for a single rotational frame. Wind simple form is available. Okay, this is all about incompressible flow. For compressible, rho simple form, steady state simple solver for laminar or a turbulent runs in for a compressible flow. Okay, rho simple C is the corrector in the simple algorithm, so that class of solver is available. Okay, sonic form, sonic liquid, rho pimple form for different class of the applications is available. Okay, rho porous MRF LTS pimple form, okay, for MRF and HVAC application. Rho porous MRF for run steady state for HVAC applications. Okay, this is transient. Wherever, please understand, wherever is simple, you understand is steady state. Wherever you see pimple or piezo, it is transient. Okay, it's very simple. Okay. Rho central form. Okay, so it is come with the particular class of the solver, it is density based solver. So if you want to build up a new density based solver, so look, if you are aware, in compressible environment, either you work with the density based algorithm or a pressure based algorithm. Okay, if you are working with a very high speed flows, so sometime the density based algorithm facilitate much faster convergence as compared to the pressure based. So stick to the density based type of the solver. This is center form DYM form. Okay, so where there is a DYM, that means it has a capability of mesh movement. Okay, so that is how you can see. This is sonic with the mesh movement capability. Okay, so wherever dynamic mesh DYM, that means dynamic mesh movement. Okay, so wherever you find any of the form has a DYM, it is coming with the mesh movement capability. Okay, then heat transfer wise bound to simple form. Okay, then you have Bossiness based also simple algorithm is available. Then you have a, this is multi zone type of or multi-zonal conjugate heat transfer. When we talk about conjugate, you have to solve the equation in solid phase as well as the fluid phase. So for that, this is very important solver. Okay, then you have Bossiness approximation based solver available, transient as well as steady state. Okay, so this is about the heat transfer type of the things. Okay, then electromagnetic, you have a basic MHD form available, magnetohydrodynamic. Okay, you have a electrostatic form available. Okay, then stress analysis, solid displacement form available. Okay, so if you want to look at very basic stress analysis, something is available for you. Direct simulation of Monte Carlo methods, DSMC form is available. Okay, then DNS, if you are talking about the DNS application, then DNS form is available. Okay, molecular dynamic method, if you are talking about the molecular equilibrium form available, MD form is available. Multi-phase flow, bubble form, cavitation form, compressible interform. Okay, so interform, when you see the interform is coming with the VUF enable. Okay, so either interform, this is compressible interform, this is incompressible interform. Okay, so wherever interform, it is coming with the VUF enable things. Okay, interdynamic, that means it is a interform with the mesh movement capability, intermixing form, interface change form. Okay, LTS, local time stepping method based some interform is available to look at the faster convergence. MRF interform, moving multiple frame of reference based interform available. Multi-phase flow with the multiple reference frame. This is all for rotating. So we need not to exactly rotate the entire mesh or anything or the part of the mesh, but we try to mimic as a source term in the Navier-Stokes equations. Okay, then multi-phase interform, porous interform, this all different class of the multi-phase flows is available. Okay, two-phase Euler form, it is so many people are working with this, and so many customization also people did with this class of the solver. Okay, then combustion wise, cold chemistry based solver is available. Okay, diesel engine, diesel form, I am very weak in combustion, so I never use this all the solvers. Okay, but this all capability is available. Okay, reaction form, row reacting form, okay, exi form, so many solver is available. Particle tracking wise, cold chemistry form. Okay, so if you are looking at how the particle is going to behave in the any fluid flow or heat transfer phenomena, you can add up these facilities from here. Okay, so this all different class of the solvers is available with you. Okay, this is all different class of the physics. So you look at so many physics is available, but that is bundled in certain class of the solver or certain class of the applications. Okay, but it not necessary whatever we are looking at is readily available in one application, so we have to adapt from different environment. Okay, so that is how it going to work. Then mesh generation. So mesh generation wise, if you think with the OpenFOAM, so two facilities available. One is the block mesh, okay, and another is the snappy hash. So block mesh is nothing but very simplified geometry mesh generator where you have multiple block and it give you the Cartesian mesh. Okay, so it is like a structure type of the meshing you can create with the help of the block mesh. But snappy hacks, you can create any class of the geometry, complex geometry you can snap with the help of the snappy hacks, and it is called the cut cell type of the mesh. Okay, so when we explore, you have idea. Beauty about this snappy hacks is it run in parallel. Okay, so that is its strength. Even the mesh generation is also you can handle with the parallel computing environment. Why it's required? Let's say you have to generate the mesh on very entire car SUV or something, where you are expecting something like millions, 30 million, 40 millions mesh size, then it's not possible to create a mesh on a single PC. Then for that purpose we require the parallel computing environment, and we create a very sophisticated mesh. And I seen this snappy hacks at ESI. People create a very nice mesh for their live project, okay, and it never fail, I say. Okay, but you have to have a sophisticated understanding about the snappy hacks. Okay, along with that, it give you the certain more conversion utility. Like if you have a fluent mesh, you can convert fluent mesh to the form. Okay, if you have a star CFX mesh, you can convert CFX mesh to the form. Okay, ANSYS mesh, IDEA mesh, Kiva mesh, Plot 3D, star CCM mesh. Okay, you can convert all this mesh in the form environment. Okay, it's ready to go. So if need not to create again mesh in for particularly for OpenFOAM. Okay, then some mesh manipulation utilities we going to explore, like check mesh. Give you the idea either that mesh is valid for OpenFOAM or not. OpenFOAM try to check different aspect of the meshing, like its aspect ratio, skewness, all these thing, and the volume, either it negative, positive volume. Okay, if fail in the checking, then immediately OpenFOAM give you the error that this mesh is not suitable in OpenFOAM environment. Okay, and you have to modify this mesh. Plus, believe me, if you are working with the turbulent flow, okay, and you created a mesh, a boundary layer mesh, OpenFOAM going to give you the aspect ratio error, but no worry about that part, because it is boundary layer mesh. You can modify that mesh by increasing the element size in the stream-wise direction, because on the cross stream-wise direction we have boundary layer. Okay, so wherever boundary layer we have very thin layers, so we cannot able to capture otherwise proper boundary layer. So for that, OpenFOAM going to give you the warning or the error, but no worry, you can work with that. But if OpenFOAM give you the error about the skewness, please don't work with that mesh. You have to change the mesh. Okay, merge mesh, you can merge different mesh. You mirror mesh. Set is the mesh manipulation utilities. It try to give you the idea how to create a different zones. Okay, set to zone, topo set, all these are utility to manipulate the mesh. Okay, rotate mesh, move dynamic mesh, move engine mesh, create patch, auto patch, all these facilities is available to create a different or manipulate a mesh whatever you created. If this utility is not available, then what it is required, you have to go back to the mesher, again modify it and come back here. Okay, let's say you want to rotate the mesh. Previous you think, okay, my stream-wise direction is X, but I want in the Y. So either you go back to the mesher and change the mesh, but with the help of rotate mesh, immediately it will rotate. Okay, so this is all about mesh manipulation. OpenFOAM is come with certain class of the turbulent modeling. So RANS based model available, LES based detached eddy is called DES, and the DNS. Okay, if you walk through this particular feature link, okay, or OpenFOAM org and turbulent feature turbulent, you will see n number of turbulent model that is coded in OpenFOAM environment. And please believe me, whatever the most used turbulent model that people use till now, all are coded in the OpenFOAM. Okay, but please don't try straight away start using it and comparing the result. I say whatever you want to adopt from the OpenFOAM, first make sure your understanding, maybe that whatever they coded is correctly, but for different class of application, maybe you have to tune certain parameter. So before you readily or try to use OpenFOAM for any of your project, thesis, or any commercial purpose for your industry, I suggest first benchmark it, try to verify the result is coming correct or not. Okay, in the similar line, LES, different class of the options is available in OpenFOAM, and direct numerical simulation is available readily. Okay, it come with certain class of models, Newtonian, sorry, this is title is different, Newtonian fluid or non-Newtonian fluid point of view. Different class of rheological model is also available. Okay, Newtonian power law, interface property, so many things is available. Okay, then transport wise, if we talk about the incompressible flow, as far as transport property is concerned, what we require to set a Reynolds number, we require the density and the viscosity. Okay, and here we're going to work with the ratio of viscosity and density, kinematic viscosity. So only nu or kinematic viscosity is required to set a transport property. But if we talk about the compressible flow, then we require certain more properties. For that, basic thermophysical models is available. So enthalpy based model is available, okay, as well as sensible enthalpy based model is available, okay. So internal energy base available, enthalpy and the rho is the density base, okay. So pure mixture, all this thermophysical model is available, so you need not to code, it is readily available. But sometime, let's say you want to change this modeling style, like right now we are saying, let's say temperature is only depend on certain thing, but later on you apply some electromagnetic force and temperature is also depend on electromagnetic force, then you have to change these certain libraries, okay. Lagrangian particle tracking is available with the OpenFOAM, okay. So Lagrangian theory based certain libraries they created, and you can adopt that library and try to look at the Lagrangian particle tracking, like in different version of the applications, okay. Then when we talk about the pre-processing as a mesh generation solver and the post-processing, so without post-processing our simulation is not complete, okay. So no worry with the OpenFOAM. OpenFOAM come with its inbuilt or adapted ParaView as a post-processor, and inside the ParaView there is a this ParaView is basically a open source, and in the OpenFOAM they created wrapper over the ParaView and it's called ParaFOAM, okay. So we're going to work with the ParaFOAM, but in the background there is a ParaView is working, okay. So it is use the VTK toolkit, okay, and it going to work with the VTK format. But when we work with the ParaFOAM, you need not to create the form to VTK and create this form to VTK utility, but it try to adapt very quickly with the help of the ParaFOAM, okay. So ParaView is our post processor. Not only that, if you want to, let's say, do the post processing in your own post processor, let's say you have ANSYS Fluent, and if you think I can do the post processing in ANSYS Fluent environment, then you have to convert the form data and form mesh to the Fluent, and when you run certain utilities, it try to create case and data file, you adapt that case and data file and do the post processing either in the, let's say, ANSYS any environment. If you have Insight, it's the very good post processor, you use that. If you are TechPlot, you use that for post processing. No need to stick to the ParaView, okay. If you have any of this class of the post processor, you can adapt it and try to use all this post processor. So this is just its GUI, how it look like, okay. Later on we explore. It is very simplified way of looking the different graph in this ParaView, okay. Runtime post processing is very important. Let's say simulation is going on, how you can see that my simulation going in the correct direction or not. For that, it is called the co-post processing or co-processing, okay. So runtime post processing facilities available, like file of a sample data can be written in for a graphical plotting, file for a force coefficient can be written, file element of, let's say we cut a certain planes and try to look at the its isosurface or contour plot on the planes, it is available. So you need not to stop while the simulation is going on, you can see what is going. It is called co-processing. If you anybody work with the star CCM, they are much aware about this co-processing, because star CCM has this unique opportunity. While the simulation going in the background, you can see how the simulation is progressing, okay. Field average, field max min, field value, surface interpolation, forces, it is come under all the runtime post processing. Sample set, probe, isosurface, cut plane, sample patch, all this utility going to explore with the help of certain class of the tutorial. So at the end of this basic module, you are aware of almost all the out of this all maximum or important utilities, okay. So no worry about that, okay. Then streamlines, near wall field, all this thing is come under the post processing environment. You can calculate any of the variable you required, okay. Along with that, you can, as I told you, export as a third party post processing, form data to Fluent, form to Insight, form to TechPlot, form to VTK, okay, and it will facilitate in different environment as well, okay. So this is all about its entire about OpenFOAM, and just gave you the brief idea how the OpenFOAM is look like. Okay, before we summarize this session, I want to acknowledge certain people, okay, because I adapted all this material. What are you going to look at in entire this event? I adapted from certain places. So this is all the people from where I adapted this entire training materials. They open sourcely put their own tutorial on let's say training slides and all these things. Okay, so from there I adopted certain things, modified based on our training requirement, and giving you the final product what you are going to see here. Okay, so thank you for this particular session. Okay, so let me first stop it.